So first of all, ways to measure reaction rates, that will depend on what kind of substance we're dealing with. For example, if we're dealing with a solid, we're always trying to calculate the rate by measuring the variation of quantity of substance per variation of time. So that quantity of substance has to be expressed based on what kind of substance we're dealing with. So if we're dealing with a solid, most likely the mass will be taken into consideration. If we're dealing with a liquid, we may look at the volume of substance being created or being consumed. Or for a gas, it would be the same thing. So here it would be most likely for a solid, here would be for a liquid, or for a gas. When I say liquid, I'm talking about pure substance. Pressure would be for a gas. Number of particles could be for anything. And concentration would be for solutions. pH, it's where we see that. So again, based on the type of substance we deal with, we'll be looking at different types of quantities. Now, how does this translate into a problem? So example A will be dealing with a solid substance. So we have a 12 milligram piece of magnesium that reacts with 100 ml in 100 ml of a solution of hydrochloric acid at 1 mole per liter. So that is the concentration of the hydrochloric acid right over here. You have your equation. The piece of magnesium completely disappears after 4 minutes and 30 seconds. Calculate the rate of this reaction in grams per second. So they really want the rate of the magnesium because that's really the only substance that is solid and expressed or measured in grams. So here what they're going to do is variation of quantity as a mass over variation of time. Don't forget, when we do a variation, it's always final minus initial. So here we have the final mass. The reaction stops when I have no more magnesium. Initially, there was 12 milligrams, which they converted into a number of grams because they want the answer in grams per second. So final minus initial for the mass of magnesium over final minus initial for the time. The whole thing lasted 4 minutes and 30 seconds, but they want it in seconds. So 4 minutes and 30 seconds converted into seconds only gives me 270 seconds. So delta mass over delta time gives me 4.44 times 10 to the negative 5 grams per second. Question 2, or B, calculate the rate of this reaction in moles per second. Here they make it a little bit more complicated. You can basically take this answer here, which is in grams per second, and just convert your grams directly into a number of moles. So the molar mass, as they stated here for magnesium, is 24.305 grams per mole. So I could only do this divided by 24.305 grams per mole. And I will get exactly the same answer as they get over here. What they do is that they do the delta mass, convert it into an amount of moles, and then they take this and they divide it by the amount of time. So they have an extra step for nothing. Like I said, if you take your rate in grams per second and convert it directly in moles per second, it does the same job and it's much faster and easier. Okay, example number 2. In this case, we're going to be dealing with a gas. So hydrogen is escaping from a reaction site in example A. So it's the same reaction, but now we're dealing with the hydrogen part. And it's collected and measured by water displacement every 30 seconds. So you have your time here, and you have your volume of gas. So it starts with no gas because we're looking at a product. So we start at 0 milliliters. And after 270 seconds, we have 40 ml of gas. So they want to know, what is the rate of production of hydrogen in milliliters per second? In this case, my units are already in milliliters and seconds, so there are no conversions to be done. All I need to do is final of quantity minus the initial quantity over final time minus initial time, which is what they do over here, and they get 0.15 milliliters per second. So that's pretty simple. In B, they want you to graph the whole thing. There's no mystery to this. You just take the data, you put it in the graph, and away you go. Example number 3. So in this case, they want you to calculate the reaction rate when the substance is an aqueous solution. So you have a different reaction here. You have a reaction between bromine and formic acid over here. At the beginning of the reaction, the solution is dark brown color, has a dark brown color because of the bromine, and the concentration is 0.0120 mole per liter. As the bromine is consumed, the color of the solution becomes lighter. Why? Because there's less bromine, and it is the bromine that's making it brown. After 5 minutes, the concentration is 0.0042 mole per liter. So this is still for bromine. Calculate the reaction rate of aqueous bromine in moles per liter second. So I already have mole per liter, I'm just missing the time. And the time they said was 5 minutes, but because they want it in seconds, we're going to have to convert that. So 5 minutes in seconds, 5 times 60 gives me 300 seconds. So my delta T is 300 seconds, final minus initial. And for the concentration, we finished with 0.0042 mole per liter. And we started, the initial one was 0.0120 mole per liter. That was the initial concentration. So again, we do final minus initial. Now don't forget, in this case, because we're dealing with concentration over time and we're dealing with a reactant, we will put the negative sign in front. Why? So we can get a positive rate. Rates are always, always positive. And here, when I do final minus initial, I get a negative concentration because it's being consumed. So the delta concentration will be negative, but will become positive because of this negative sign in front. So that's what this is for, is to make sure that the final reaction rate that we're getting will be a positive value. So delta concentration over delta time gives us, for bromine, this over here. And that's pretty well it.